Okay, so now that we know how to convert coordinate systems in general for multiple integrals, let's go ahead and work through an example. So we're presented with this integral that is in the variables x and y, and they've given us some new variables to convert the x and y to, and they've also given the region described to us r as a parallelogram in the xy plane. So let me get this set up and we'll kind of see why we would want to change variables anyway. All right, so take a look at this parallelogram R. It doesn't easily lend itself to either type 1 representation or a type 2 representation. It's worth kind of thinking about that for a second. So if I was to represent this as a type 1 region in x and y and integrating over it, then I would need to split it up into two pieces. I would need to first integrate over this triangle with this being the top function and this being the bottom function, and then this other triangle with this top and this bottom. So that would be an option for type 1. And then type 2 is actually a worse situation. So if I'm going to view this as a type 2 region, I would need to split it up into three different pieces, where this is the right function and left, and finally right and left. So I don't want to do either of those things, and that's usually the motivation for switching variables. Let's go ahead and see how we convert the region over to the new variable system, because that's at least one thing that I have to do. I have to convert this region over, I have to convert the integrand, and then I have to figure out what the dA unit is using the theory from the last video. So a general method for converting the region expressed in the old variables to a region expressed in the new variables is to express the boundary instead of in terms of x's and y's, is expressing those boundary pieces in terms of u's and v's. So let me show you how to do that. All right, here's what I'm going to do. I'm going to look at the boundary pieces one by one. Let me actually number them. 1, 2, 3, and 4. And I'm going to express those boundary pieces as functions in terms of the old variables. So they're obviously lines, and I've got the points that they connect, so I'm going to go ahead and produce all of those lines. Okay, so I've represented each of the pieces of the boundary of the region in terms of the old variables x and y. Over here with the conversion equations, I don't want to deal with fractions, that's annoying. So I went ahead and multiplied both sides of the conversion equations by 4, and I'm also going to, I think, multiply each of these equations by 4, and then I'm going to swap out the x's and y's for the u's and v's. Okay, so one more step down here. Okay, now what I'm going to do is I'm going to replace, every time I see a 4y, I'm going to replace it with this, and every time I see a 4x, I'm going to replace it with this in each of these equations. And that will convert the boundary pieces from being expressed in terms of x and y over to pieces that are expressed in u and v. And just an observation before I do that, the conversion equations are linear in the variables u and v, which means that I expect a parallelogram or a quadrilateral to come out of this conversion. In terms of linear algebra language, this is a linear transformation of the old system over to the new system. So I could instead just convert the 4 points from xy to uv, but the reason I'm doing this longhand method is because you're not always guaranteed to have a linear transformation like this. So I'm not guaranteed to have straight lines produced through the transformation from straight line boundaries in the original shape. Okay, so let me go ahead and convert. All right, so we're all done. You can see someone had very cleverly chosen these conversion equations so that the boundary pieces of the region R are actually much, much better in the variables u and v. Let me write this in terms of linear, in case you're in linear algebra right now, let me write this transformation in terms of a matrix multiplication, just as a side note. So these two linear equations can be represented like this. Okay, and the idea here is that if you take a region in the UV plane and apply this linear transformation defined from this matrix, then you get the outputted region in the XY plane, which is pictured here. So that's just a little bit of a side note. Let me go ahead now and visualize the region in the UV plane that's produced through this transformation, and then I'm going to integrate over it in the variables u and v. Okay, so see how much nicer the region is in the UV plane? It's simply, I think it's a square, yeah. So let's go ahead and represent the region using inequalities in our new variable system. Way easier than expressing the original region as a type 1 or type 2 in the variables x and y. Okay, so let me remind myself about the conversion unit over here. I need to compute the Jacobian of the transformation. As long as I have the old variables in terms of the new variables, I just take the appropriate partial derivatives, compute a determinant, and take the absolute value. So I'll do that now. All right, so there you have it. This is going to be the differential unit I need to place in the integral when I convert from the xy over to the uv. Okay, I think I have everything I need, so I'm going to go ahead and convert the integral. Okay, and then we just have a simple iterated integral to complete at this point. Use your favorite method. There it is. I think that obviously the most complicated part of these conversions is converting the region. And as I mentioned before, if you're confident that the output of the transformation of this parallelogram is going to be a parallelogram, it's slightly shorter to just convert the xy points over to uv points. But again, a word of warning, your transformation isn't always linear, so it's not always that quick transformation. You could just go through the boundary pieces one by one and convert them to the new variable system by using the conversion equations.